Right, chemists, happy Friday, happy Friday. So the plan looking ahead, I plan on finishing chapter 15 today. Yeah, I don't have 16 ready, so whenever 15's done, we can just be done for the day. I hope to finish it with enough time left. I have a demo here that I kind of scrapped together. So finishing, chemical equilibria here. I sent that announcement yesterday about midterm 1 resources. So at this point, it's in your hands. It's in your hands. You have all of the resources to be successful, all right? So I'm writing the exam right now. We're going to have the exam on Friday, next Friday, like a week from today, and it's going to cover all of chapter 13 through 15. And what we'll see here in a little bit is I'm pulling a lot of chapter 14 material from kind of teasing that out of this chapter, chapter 15 chemical equilibria. There's a lot of overlap here. So having a really firm understanding of reaction rates, chemical kinetics will help you in this chapter in chemical equilibria, because when we make adjustments, we change rates as well. And that's a big learning objective within this chapter. So 5 practice midterms I posted. Since we're covering all of the material, all of those questions are free game. For the midterm, I don't know. All the information's on that page, right? Like the supplemental packet, which is essentially the first page of your recitation. That's exactly what you'll get. It will be a Carmen Respondus lockdown browser quiz. So there's a Respondus test quiz for you to test out your lockdown browser, but all of the practice exams are not under like lockdown browser. So there's 3 Carmen quizzes where if you take it, you can look at the feedback, and Dr. Foose has given really great video feedback for all the questions. And then I have 2 paper exams that I just wrote the keys on it, so you can see that. All right, so any questions about, so my plan, that's actually, I was gonna say that. The question is, well, what are we gonna do on Wednesday? So remember, we don't have class on Monday, but on Wednesday, that is one last day before the midterm. My plan is to maybe do like 45 minutes of chapter 16 and then do midterm review. All right, because I don't want to spend all that, I don't want to run out of time at the end of the term. So I want to use this little bit of extra time, but I do want to give you that chance to review a little bit. So I won't take it all the way to the end. I'll devote at least half the class to midterm review. And I will send out information about the Zoom session, the midterm review Zoom session. Did we agree Tuesday? Is that what we said, Tuesday? And I'm going to record it. I will post it. So if you can't make it on Tuesday, you'll have Wednesday and Thursday to watch it. All right, and then I'll post a new activity or something to do. I have a lot to do this weekend. All right. Okay, so chapter 15, we left off talking about big K. So the equilibrium constant, which we realize is all based upon the fact, so I'm just gonna in the corner here review, big K is your concentrations of products over reactants at equilibrium. How we derive that is that we say at equilibrium, the reaction rate in the forward direction equals the rate in the reverse direction. And so relating this to chemical kinetics, your overall reaction rate is equal to the rate constant. So this is small k, right? K forward times the concentrations of your reactants, right? Versus your overall rate for the reverse reaction is K, little k rate constant in the reverse times your concentration of your products. All right. And so where big K comes from, equilibrium constant, is if we derive this and move things around, we get, if we divide both sides by K reverse, and we divide both sides by your reactant. So what happens is that cancels, you get that Kf over Kr equals the concentrations of products over reactants. This is equal to big K. Sorry, this is like really messy, but I just want to kind of overview this. This is big K. I'm just going to call it KC. That's how we derive it. So your equilibrium constant is telling you, okay, the ratio of your rate constant in the forward direction over the rate constant in your reverse direction. But it also tells you the relative amount of products and reactants that you have at equilibrium. That's the big idea here. And so K, big K, is those numbers are dependent on the temperature and the reaction that's taking place. So K is a constant, and it always describes equilibrium conditions. And so these two questions that we did here is I give you, you know, amounts of substances, and I ask you to calculate your equilibrium constant. And so the big idea here is we use an ICE table. So given, you know, a little bit of reading comprehension here, recognize that these values given first are initial concentrations, and then I tell you, hey, you like add all this stuff to a vessel, then it changes so it gets at equilibrium. We measure a equilibrium concentration of one of the substances, so we fill in that in the equilibrium line, the NO concentration is equal to what's given here, and that allows us to fill in the rest of our ICE table of all the other substances. And the big idea here is that the E line, the equilibrium line, is what dictates the number of your K, your big K equilibrium constant equation. And so what we get here, oh, I should delete that, sorry. When you plug in all these numbers, all right, that you calculate what X is, and then you kind of put all of those back into this equation. Do I have these? Do I have these? Yeah. So what we get is when we put X back into the E line, that the amount of H2 gas we have at equilibrium is 0.012. X is 0.019. That's the amount of N2 we have. And then putting X into your water concentration, there's 0.138. So those are all molarities. That is, nope, not that number. This number is NO. These are the numbers that we're putting into our K expression with the correct exponents and so forth. So Kc in this reaction is equal to the concentration of H2O, but then what's missing? Squared, times N2. So products over reactants. NO squared H2 squared. So then at this point, it's just plug in those numbers that we just got. So H2O is 0.138 squared times N2, 0.019 over NO is 0.062 squared, and then H2 is 0.012 squared. All right, and then so what you get from that, I think, is this number. It's about 600. All right, so based upon that K, is there more products or reactants at equilibrium? On that K value. More products, yeah, because K is a really big number. And again, if you just kind of in the back of your head understand that K is equal to the concentration of products over reactants. If K is a big number, that numerator also has to be big. All right, so there's another way we can use an ICE table where I give you initial conditions and you calculate your K value. I typically have to give you at least one equilibrium concentration for you to fill in the ICE table. You could not answer this question if I just gave you the initial line. You could not answer it. And if I said, hey, calculate K, you couldn't do it because you don't know how, like, to what extent the equilibrium goes. I have to give you at least one of the equilibrium numbers so you can calculate everything else. So that's kind of the strategy there. Example 3 is the same as example 1, so I'm sorry. All right, so let's look at other applications of the equilibrium constant. All right, so this is, the question was kind of before, you know, how can we predict the direction a reaction goes? Because like in this example, this one, right, we did this one. We started with reactants, and I asked you which way does the reaction have to go? It has to go to products, That one, it's kind of clear to see which direction it goes. But what if we had stuff on both sides? Then it's not so clear. But there's a way for us to predict it, and that is using the reaction quotient. All right, so the reaction quotient is called Q. It's the exact same equation as K. The only differentiation is that Q, this number that we get out, is our concentrations. We put in concentrations that are not at equilibrium. That's the big idea. K, that value is based upon concentrations that are at equilibrium. When you calculate K, you're putting in non-equilibrium concentrations. That's the big idea. So here, if you try to if I give you a bunch of concentrations for something and you get that Q equals K, that means you are at equilibrium because your concentrations of stuff are in the correct ratio. But let's say Q is less than K. You plug in concentrations, you get a Q reaction quotient that's less than K. So let's think about it. So Q is a smaller number. Remember, Q or K, whatever, it's always equal to products over reactants. So if your Q is small, you have too much of what? If Q is small, your denominator is big. So you have too much reactants. So which way will your reaction go? Forward, right, to make more products, to make the number, to make Q approach K. Does that make sense? And that's what it says, right? If Q is less than K, forward reaction must occur because you want to make more products. Again, I don't memorize like these things. I just understand that Q is the concentrations not at equilibrium, and I ask myself, how do they have to change to get up to K, or like to reach K? Versus, what if Q is more than K? A bigger number. What do you have too much of? Products. If Q is a bit bigger than K, you have too much numerator, products. So how will the reaction adjust itself to make that number smaller to match K? It'll do the reverse reaction. You'll make more reactants. And that's essentially the principle behind Le Chatelier's principle that we'll learn about later. That's basically it, all right? More products. So in this case, we need to make more reactants. And again, I told you, if you just kind of remember this, products over reactants, you'll be good, all right? So Q is just things not at equilibrium conditions. So let's look at this reaction and predict which way the reaction will shift. I'm telling you that for this generic reaction, the K, so equilibrium concentrations is 1.5. So for fun, let's just write what that expression is. K, C for this reaction is the concentration of AB squared times A times B, or over A times B, right? That's K. And I'm telling you the ratio at equilibrium is 1.5. I just made up a number. Okay, so so these are equilibrium concentrations. If we have a system at equilibrium, it should equal 1.5. So with these different pictures, let's kind of predict, are they at equilibrium or not? So what we need to do is count the things. So let's do the middle one first. So we have red balls, blue balls, and that. So how many ABs do we have in this middle vessel? 3. How many A2s? 3. And then how many B2s? 2. So putting those numbers into our K expression, okay, this would be what? 3 squared over 3 times 2. That equals 9 over 6. This equals 1.5. So which way will this reaction go to achieve equilibrium? It's already at equilibrium, yes. So because Q, the values we put in, it equals K, we're at equilibrium. So if we just let that reaction go, the concentration, the number of those molecules aren't going to change, all right, of each of those. It'll kind of maintain those numbers of molecules of each. Okay, so let's do the other ones where we actually do predict a direction. So this one's at equilibrium, so nothing's going to shift. All right, so let's do the left one. Let's do this one. Okay, how many ABs are there? 6. How many A2s? 1 and 1. All right, so plugging these numbers into our K expression, but remember, this is called Q because we may or may not be at equilibrium, but it's still the same calculation. 6 squared over 1 equals 36. Okay, so Q compared to K is much bigger. We have too much of what? Yeah, so Q in this case is much bigger than K. All right, and again, remember, it's products over reactants. So if Q is too big, we have too many products, too much products. So the reaction is going to go in what direction to get Q to become K? Reverse, yes, too much product. So we will go, to the left. Left, it'll shift to the left. Or to the reactants. We'll make more reactants. We'll do the reverse reaction. All of those things are synonyms with one another. Okay, let's do the last one. How many ABs are there? 2. How many A2s? 3 and 3. Okay, so doing this, it's 2 squared over 3 times 3. So 4 over 9. 4 over 9. I don't know what that is. It's about a half, whatever. But anyway, Q in this case is greater or less than K? Less. So we have too much of what? Reactant. So the reaction needs to go in what direction? Forward. We want to make more products. Okay, you see how all that works? So that's how calculating Q will help you predict which direction to go. So going back to, if we want to go back to this example we did this one, okay? If we went back to this example, see how I gave you concentrations of like a lot of things? But since there was no N2, we predicted, oh, the reaction has to go this way. Pretend I gave you initial concentrations for everything. If I gave you something like this, all right, and you set up your ice table, the first idea here is that you need to figure out which direction the reaction has to go. Typically, we already give you K, and I think we'll do some examples here in a little bit. If you're given initial concentrations and a K value, you can just quickly back of the envelope calculate Q to figure out which direction the reaction has to go. All right, so that's the idea here. Because here, me personally, I can't just look at that and be like, oh, I know which way it goes. No, I have to calculate Q. All right, are we going to do examples here? Yes. Okay, so we estimated Q to help us predict which way the reaction goes. All right, so here's this one. Yeah, it's exactly what I just said. Here, I give you initial conditions of everything. I give you K. We need to calculate your equilibrium concentrations. So we're still using an ice table. So note here in the previous two examples, we calculated K. This time I give you K. So this is just a different way we can ask questions. So filling in our ice table, these concentrations just go straight in there into that I line. So 0.5, 0.1, 0.1. I'm just going to drop sig figs because I'm lazy. All right, so can you tell me which way the reaction's going to shift? Like just looking at that? No, I don't know. So the method here to determine, oh, well, like I know I'm going to like lose or gain an X amount of AC2. I'm going to lose or gain an X amount of A and C2. But I don't know, is it going this way or is it going the other way? Like, I don't know. So this is where we need to calculate Q. All right, so you just back of the envelope, put in the numbers in your I line to figure out, okay, what's the ratio of products over reactants? So in this case, Q is 0.1 squared over 0.5. Is that what we got? And so you get that Q equals 0.02. So based upon that, Q compared to K, which one's larger? Q. Q is larger. So what does that mean? We have too much of what? Products. Q is too big, the numerator is too big, so the reaction is going to shift what way? In the reverse. So where will my negatives go in my change line? The negative signs. Yeah, it's going to, since the reaction has to go this way, I'm going to consume products and I'm going to gain reactants. See, if you get the direction wrong, you can still solve it, but your numbers will be off by a negative sign, and that can be very confusing. So if right off the bat you can determine which direction it goes, and in this case it's less obvious, because in all the other examples we had some void we were trying to fill. But in this, it's definitely less obvious. You have to calculate Q. Okay, so what do we do next? You add the columns, yes. So in my E line, I have 0.5 plus X. I have 0.1 minus X. And then I have 0.1 minus X. That's my equilibrium line. Okay. So what's the next step? What's the significance of that equilibrium line? Where do I put it? Yeah, you set those things equal to our equilibrium constant, K, right, which is the 0.001 number. All of these equilibrium concentrations relate to the concentrations of these things at equilibrium. That describes K. So we know Kc equals A times C2 over AC2. So I'm just going to plug in these numbers into the appropriate places. So what we get when we do that is 0.001 equals the numerator, it's the same number, so it's 0.1 minus X squared. Do you agree with me? Because it's just the same variable, or like the same expression twice multiplied, yeah. And then the denominator is 0.5 plus X. So I just plugged in the knowns and the E line into my K expression. So our goal is to get equilibrium concentrations. So do you see we have an expression here now with just one variable, just X. So if we can solve for X, can't we put that back into the equilibrium line just like we did before? But it's different now, because what did I put in the corner of this slide? The quadratic formula. But here's the trick. If you are clever with this topic, you never have to do the quadratic formula. There's always assumptions you can make to make it easier on yourself. So if you solve the quadratic formula, and I don't feel like doing it, so I'm just going to put it into Wolfram alpha. Okay? And I urge you to do stuff like this on homework. You never have to do the quadratic formula on the exam. You can if you want, but I'm going to show you how to make assumptions that will get you an answer pretty close. Okay, so how I would do this on Wolfram alpha is literally just put in this exact expression as written, because I don't trust myself to square expressions. I don't trust myself to do that and not mess up. So I'm just going to put it in straight into Wolfram alpha. Do folks use this? I use it for everything. Okay. Okay. So 0 point what is it? 0.01 equals 0.1 minus X squared divided by 0.5 plus X. Is that it? Is that right? Okay. All right. What does Wolfram alpha say? Okay. All right. So it gave me these two answers. 0.076 and 0.125. I don't know which one it is, but I'm going to quick go back. All right, so it told, Wolfram Alpha told me it's x equals, what is it, 0.076 or 0.125. Only one of those numbers makes sense. Just in your head, quick, put those numbers back into the E line. Only one of them makes sense. Which one doesn't make sense? The 0.125. Why? Yeah, if you put that right here, 125, you get a negative concentration. You can't have that. So we can eliminate that. All right. So that's how you would get the equilibrium, equilibrium concentrations. Do you see that? So what our next step would be is just to throw that X back into your E line and report those concentrations. And so what you get, what did I do? I don't know. If you stick those X's into that E line, you get that your AC2 concentration is equal to 0.5 plus 0.075, so 0.576 molarity. A is equal to, it's just A, is equal to 0. I have to do math. 0.1 minus 0.076 is 0.024. And that is also equal to the concentration of C. So note here, we're doing this a little bit differently. I'm giving you K. You have to give me equilibrium concentrations. This is harder. I would say this is harder than the previous ones that we did, where I had you calculate K, in my opinion, because it requires the quadratic formula. Sometimes. Okay, so the next, can I move on? I want to show you stuff about quadratic formula. So yes, if you solve the quadratic formula, you get that answer, all right? But there's a lot of places to go wrong on the quadratic formula, and I realize that. But I will always give you the formula for the quadratic if you want to use it. But you have to put it into that, ax2 plus bx plus c form equals 0. You have to do that, and I don't trust myself to do that. So the nice thing about the ICE tables is that we almost always can make an approximation to help us simplify the math because we're lazy. So the idea here is this is what we stuck into Wolfram Alpha, right? This is K. So is this K big or small? Small. So we have mostly reactants at equilibrium, all right? So with that idea, K is really small. So if we let me just quickly go back here. If we, have this reaction going on, K is fairly small. So won't the reaction mainly stay on this side of the reaction, right? So this plus X is actually a really, really small value because it's not changing that much to go forward. So since K is really, really small, I make the approximation that the reaction stays on the reactant side, so we can actually ignore that plus X. That plus X. All right, because it's really small. Or you can think, 0.5, it's already a really, really big number. Right? So that's the approximation here. And so when you put it in, if you put this straight into Wolfram Alpha, you get X equals 0.079, and I think that's what we said was the correct answer. This one didn't make sense. Versus if you make the approximation that X is really small, right? And so if you put this into Wolfram Alpha and solve it, so in this case, how would you solve for X here? Is it a quadratic? No. You multiply both sides by 0.5, then you take the square root, and then you just add or subtract or whatever. So it's not the quadratic. You can do that fairly easily. This is the solution. And again, there's two answers because when you take a square root, you get the positive and the minus version, but the positive side is the chemistry part that we use. Look at the two answers you get. And look at the two answers you get when you actually do the quadratic formula. Are they that different? Not really. It's actually less than a 2% difference, which is fine. As long as our answers are within 3%, they're fine. Okay, and so how an exam will be, if I asked you for equilibrium concentrations, the possible answers will always be far enough away from one another that if you make an approximation, you will get that, like you will clearly know which one's the correct answer. All right. Okay. So do you see where the approximation came from? That K is small. Your reactants, there's lots of reactants, so that plus, that usually what we do when we make an approximation is we try to get rid of that X in the denominator. That's what we try to do. All right, so that's that whole idea. So this number is basically very, very similar. You would get, you know, very similar answers. Your answer would be close enough for on an exam because, you know, I'm not asking you for these types of questions to put in an actual number. And even then, if I ask you to put in a number, I always put a tolerance on it, like a rounding, like a, you know, 2, 3, 4% tolerance on all my answers in case for rounding. But yeah, I will show you examples on how we can make those approximations. Yeah. So this, yes. So if I had a K of 1, can we like say that the reactant, there's more reactants or more products if K was exactly 1? No, they're pretty much equal. So yes, we do want like a fairly small K or a fairly big K. This example is kind of on the cusp of that. I don't think this K is small enough for this example, but we see examples where like K is to the 10 to the negative 20. And in that example, oh yeah, it's small enough that you can ignore the X in the appropriate place. So let's look at another example. All right, this one. Okay, so here is another thing. So let's set up our ice table. Okay, here are my initial conditions. So I have 0.1 molarity AD, 0, 0, A and D. Okay. Well, first off, we need to predict which direction it goes. Do we need to calculate Q here? No. The reaction has to go to the right. So minus X plus X plus X. Right? Or you could calculate Q. If you calculated Q, Q's 0. And it has to go to the, it would have to go to the right to be a positive number. All right, and so then we add up our E line, so 0.1 minus X, we have X and X. So those are my equilibrium concentrations. I give you a Kc, it's right here, okay? And so now we just set up our equation. We set up Kc equals A concentration times D concentration over AD. All right, now we plug in the numbers. So K is a really small number, 3 times 10 to the negative 10 equals A squared over 0.1 minus X. So again, this is a quadratic. But let's use our intuition here. K is really small. So at equilibrium, there's going to be a ton of reactants. So this contribution, so AD is a reactant, right? Are we going to lose a lot of AD? No. So my assumption is I'm going to ignore this. So I can rewrite this expression as 3 times 10 to the negative 10 equals X squared over 0.1. Because I'm saying, like, we're not going to lose a lot of that AD reactant. It's mainly going to stay on the same side. All right. So, do you see how I made that assumption? Can you solve this? Yes. Which one would you rather solve? The second one. Yes. But prove it to yourself. Put both of these into Wolfram alpha. You will see that X is basically the same for both of them. And the reason is because we're using our intuition here. We're not just making assumptions willy-nilly. We're making them based on some things, based on the fact that K is really small. The reaction's mainly going to stay on the reactant side. So this we're not going to lose a lot of reactant. It's going to stay on the reactant side. And so what we get, do I have them? No, I don't. I can put it into Wolfram alpha and we can check it out. So I get that X equals, if I do the assumption, this is the assumption, all right, or the approximation. I get X equals a really tiny number, 5.4 times 10 to the negative 6. All right, and so what are we trying to do? Oh, calculate equilibrium concentrations. So recognize that with that X value we just got, we plug that back into these E-line to get equilibrium concentrations. So this number, 5.4 times 10 to the negative 6, is equal to the concentration of A and the concentration of D. For fun, put this in your calculator, 0.1 minus this number, and tell me what it is. What is it? It's basically 0.1. Like, did it change, like the amount it changed, did it really even change that number? No, and that's why this approximation works, why it's valid here. We're not losing that much reactant. So for fun, I told you I'd put it into Wolfram alpha. Okay, so we'll put the full one in. So what is it? 3e negative 10 equals, just x squared over 0.1 minus x. Okay, so what's the answer there? Okay, do you see that? 5.47 times 10 to the negative 6. What was the answer we got? 5.4 times 10 to the negative 6. Close enough? Is that close enough? I think that's close enough. We're at the same order of magnitude. That's close enough. But for fun, so what is it? 5.47. So let me just take out that x and just I'll let it solve it for me. But that's this now is not a quadratic. You can just very simply, oh wait, no, it's the same number. It's literally the same number. So when I took out that minus x at the bottom, it's like, I think when I wrote my notes, I just rounded poorly. So it is the same number if you make that assumption. So trying to get you to think about how to utilize your time the most efficiently, yes, you can absolutely just distribute all of the squares and get your equation into like a quadratic form and do the quadratic formula if you want to take that time to do it, but you don't have to. As long as you make approximations that work. All right, so let's just do one more. One more. All right, so this one's pressures, but it's the same thing. I give you everything in pressures. So I have N2O4. Oh, we're going to do this. We're going to do this in a little bit. N2O4, this is a white substance. NO2 is brown. No, okay. So here are our concentrations, 0.5, 0.5. Oh, sorry, they're pressures, but that's fine. Calculate equilibrium concentrations. So what's our strategy here? It's the same. It's always been. We need to predict which direction this reaction goes. These are equilibrium pressures. Can you just look at that and tell me which direction it goes? No, I can't. So we probably want to do what? Calculate Q, just to be extra sure. So Q in this case is equal to the pressure of NO2 squared over the pressure of N2O4. So it's 0.5 squared over 0.5. That Q is equal to 0.5. So how does Q compare to K? Smaller. So what do we have too much of? Too much reactant. So my ice table is going to go in what direction? To the product. So it's going to be minus x plus 2x. Where does that 2 come from? Just to remind folks. stoichiometry. Now we just add it up. 0.5 minus x, 0.5 plus 2x. That's my E line. What's the next step? The E line goes where? Set it equal to Kp, yes. And because all of these are in pressures, that's why we're using Kp. All right, so Kp equals, which is 48, equals NO2, so 0.5 plus 2x squared, very good. And then the bottom is 0.5 minus x. All right, and then you solve it. I'm just going to tell you for this one, it's probably best to use the quadratic formula in this case. So when you use the quadratic formula, you get x equals 0.458. So how I would do it if this was like a homework question is I would put this straight into Wolfram alpha, just as is. As is. Do know I would not give you a question like this one on the exam. I would always give you one where you can make an approximation. Like either a really huge K or a really, really small K. This one's kind of like in the middle. It's not super big, but it's not like super small. So I throw that straight into Wolfram alpha and I get that X is that many ATMs, and then I just throw it back into my equilibrium line to calculate what those equilibrium concentrations are. And so when you plug those X's back into the, oh wait, no, that one doesn't, no, it's right, okay, never mind. We get N2O4, that pressure is 0.042 ATM. Again, I'm just plugging in that X value. And then NO2 is 0.5 plus 2X is 1.416 ATM. And that's my answer. How do we feel about this? The math. The good thing about these types of questions, all right, these ice table ones where I give you initial concentrations, I give you K, they're literally all the same. Every single one of them. They're all the same. All the same. There's three types of people. Someone who can crank this out and recognize that there's a pattern. There's always a pattern. There's typically an assumption that can be made. They can crank it out in 2 minutes on an exam. There's a third type of person who may take 15 minutes for this question on the exam. And then the third type of person is they recognize they can't do this question on an exam setting in that time frame and they just skip it. Okay, so ask yourself what type of person you want to be. All right, remember, all questions are worth equally. And if you take 20 minutes to answer this question, I'm telling you, I give you permission to skip it and come back to it later, maybe, if you have time. I'd rather you get those like, easier questions, maybe just a conceptual one that you could get to. Yeah. Does someone know the answer? 35 to 40. It's on the midterm resources page that I posted yesterday. Everything you need to know is there. Okay. This is a long question, but if you know how to crank it out, like the combustion analysis questions, okay? What kind of person were you? Could you crank it out? Could you crank it out, or were you someone who it took time to really think about the stoichiometry going on and the molar masses, and you just decided to skip those ones? I mean, that's fine. Like, know where your strengths lie. And so I just want you to keep that in mind, that this is time consuming. But the strategy is the exact same for all of them. All right, can we move on? There's plenty of ice table practice in my overview sheets, every single one of them, and you'll see that they're all the same. They're all the same. All right. All right, so now, wow, yeah, this is the last part of the chapter, Le Chatelier's principle. So it's exactly like basing everything on Q, right? Where we said, oh, if Q is bigger than K, we have too many products, the reaction has to go in reverse. But we're gonna go into crazy detail about that and relate it to chemical kinetics and what that means for a reaction. So again, if you keep this in mind, K equals products over reactants, basically, that will get you far. The idea is, okay, what if we already have a reaction at equilibrium and we disrupt it somehow. If we disrupt the concentrations of things, are we at K anymore? No, so what equation do you use? Do you use K or Q? Q. And so the question is, okay, you're at equilibrium, you're at K, but you disrupt it, now you're at Q, so a non-K number. The question is, how does the reaction have to shift itself to get back to K? And that's what Le Chatelier's principle says. And basically, if you think about a seesaw, it'll get you qualitatively 95% of the way there. But then we're gonna look at a crazy amount of detail about that, all right? So again, we're already at equilibrium. We change or stress the system somehow, so then we're not at equilibrium anymore. We use Q, the reaction quotient instead. So Q tells us a lot of different things. We can look at the changes in forward and reverse rates, because remember what equilibrium means. The rate forward equals rate reverse. But this is only true at equilibrium. So once we change concentrations of things, we disrupt that. We're no longer at equilibrium. So we're bringing those ideas back. I will be honest, when I learned this in my college chemistry, I just learned Le Chatelier's principle and I left it at that, and I never thought about reaction rates. But this is kind of bringing chapter 14 and 15 together holistically, and I think I hope I do a fine job kind of relating everything together. All right, so this idea, this is only true at equilibrium. So we need to ask ourselves, okay, how can your reaction reestablish K? And it typically means changing rates in order to achieve that. And then finally, we'll look at like the general pattern of predicting which way reactions need to go. And that's Le Chatelier's principle. And we've already done a little bit of that already. So the stresses of the systems that we're going to look at is either adding or removing reactants or products. So we're changing concentrations. Another one is changing pressures. This is only applicable to reactions that contain gases. And then finally, changing the temperature of your equilibrium. Because I mentioned this kind of briefly at the beginning of our chapter. We know K, big K, equals the ratio of KF, rate constant, over K reverse. These small Ks typically when I talk about a rate of reaction, I mention what temperature it's at, because if we change the temperature, small K changes. So wouldn't you predict if I change the temperature of a reaction, big K changes too? So it's that whole idea, all right? And we'll come back to that. All right, so here's Le Chatelier's principle. This is just based upon, observations. Le Chatelier's principle is really qualitative, but again, it helps you predict directions of reactions like 99% of the way. We're just going to look a little bit deeper into reaction rates. So you can read those. The first one we'll look at is concentration. How I like to think of it is if you're given a reaction like this, it's like a seesaw. If you add more product, than my seesaw, which way do you have to move stuff to make the seesaw even again? You got to move it this way. Does that make sense? So if you add more product, your seesaw goes down in one way. The reaction has to move to the reactant side to make up for it. Does that make sense? Again, qualitatively. So here, how will the equilibrium shift? Just say left or right if we increase the concentration of N2. If we add more of N2, it goes in which direction? Just point. This way, yes, to the product side. So we're going to go that way. Do you see that? It's like a seesaw. But we will go into a disgustingly a large amount of detail about that. Okay, what if we decrease the amount of H2? Yes, it's going to make up for it by pushing the reaction. Essentially, if you remove H2, you're like lightening the reactant side. That's how I like to think of it. You're like lightening it. So you want to take some of those products and push it to like fill that void. So if we decrease a reactant, it is actually the reaction's going to shift to the reactant side to fill that void. Okay. What if some NH3 escapes from the vessel? Product side, because that's the same thing as saying that NH3 concentration goes down, right, if it escapes. Okay, all right. All right, do know I had to change some of these. I actually got this concept wrong, and a TA had to correct me, all right? So in this case, changing pressures of systems. So note that all of this is happening in the gas form. This is what reaction? The Haber process, that evil guy. So here we have gases being formed, right? Gases are involved. So if we increase the overall pressure of your reaction vessel, okay? So the pressure of all of the substances, it gets larger, right? So if I really like squeeze on the reaction vessel and increase the pressure, what your system will try to do is relieve that pressure, right? It doesn't like high pressure. It wants to relieve that pressure. So what side of the reaction do you think will help relieve the extra pressure that we subjected on it? The side with more moles or less moles? Less moles of gas. Yes, so if we increase the pressure, we shift to the side with less moles of gas. So in that case, we're going to shift to the products. Okay? What if we double the volume of the container? Overall pressure changes how? The partial pressures of our components, their concentration, their pressure goes down in that case. So it's the same idea. If I reduce the pressure of all of my things in my equilibrium, I want to make up for it. I want to make up for that void that I just created. So I want to shift to the side with more moles of gas. So it's the opposite of the previous one, all right? So if the pressure go down, shift to side with more moles of gas. So it goes this way. Okay, all right. All right. Now the last three. What if we heat or cool the reaction vessel? What piece of information I didn't use about this reaction yet? Right before it? It's exothermic. So I told you that Le Chatelier is just very qualitative. What I'm showing you right now is technically wrong, but it still allows us to predict it in the right direction. But I will show you why it's wrong in a little bit. So if we have an exothermic process, is heat a reactant or a product? Product, right? We feel heat, the reaction gives off heat. Okay, so if we heat the reaction vessel, are we adding heat or removing heat from the reaction? Adding. I know it sounds like obvious, but look, I put the heat part as a product. So it's like the same thing. We're adding heat, we're adding more product. So which way does the reaction shift? Just treat it like we did N2 and H2 and all that stuff. It moves to the reactant side. If you treat heat like a product or a reactant based if it's endo or exothermic, you'll be able to predict it. Do you see that? Do you see that? So it's going to go this way. Okay. If we cool the reaction, are we adding heat or removing heat? We're removing heat. So we're removing a product. So the reaction has to shift to the products. Yes. Okay. All right. And the last one, this was my misconception I got wrong. If we add an inert gas to the vessel, this one's a trick question. Because you may think, oh, if we add extra gas into the vessel, the pressure of the overall vessel increases. So P total increases. But the thing is, the partial pressures of each of the things do not change. All right, if we just add a gas, because pressure, partial pressures is related to or analogous to or proportional to moles of gas over volume. So because we're not changing the volume at all, we actually aren't changing the partial pressures of N2, H2, or NH3 when we add an inert gas. So essentially, your equilibrium concentrations aren't changing. So there's actually no shift at all because we're only changing the total pressure of the system, not the partial pressures. So adding an inert gas actually does nothing to the equilibrium when it comes to gases, right? So that's the trick question. Okay, So that's Le Chatelier, very qualitative. Let's look at it in a little bit more detail and remind ourselves what the equilibrium constant is. At equilibrium, rate forward equals rate reverse. That I can write the forward rate law, K forward times reactants equals rate constant reverse times products. These are rate laws. Do you see that? This is the rate law for the forward. This is for the reverse. Do you see that? All right. And so from this relationship, we get Kc, our equilibrium constant, where we have products over reactants. So let's pretend we add H2 to this reaction. Based upon Le Chatelier's principle, which way does the reaction shift? To the products. Yes, that's what it shifts. But let's look at the details of the rates that happen. Okay, so this, if we kind of zoom in right here and see what's happening, we add H2 to the reaction. But look, we have to follow stoichiometry. If we shift to the product side and we make more products, that's what you see here. So like instantaneously we add reactants and some product is made. But in order to make products, we have to consume reactants, don't we? So in this example, what you see is that we add like instantaneously some H2, product is formed, N2 is consumed because it has to be to make product, and also H2 is consumed. So this is kind of how the concentrations are changing with time. Now let's look at the rates, okay? So this one's a little bit tricky, this first one. At this moment in time, right here, when we disrupted the system, is the forward rate or the reverse rate larger of our reaction? You told me when we add H2, Le Chatelier predicts the reaction goes to products. So which rate has to be faster? It's rate forward or rate reverse? Which rate produces more products? The forward, yes. Yes, but I'm going to show you why the forward rate is larger. So at this moment, because at this moment, are we at equilibrium right here? No, we are at Q right here. Here, before, we're at K, and that's fine. But at that moment of time of Q, the forward rate is actually larger. And there's a reason. There's a reason here, all right? Because, so actually right before that, so when we are in this equilibrium, the forward rate is equal to the reverse rate, right? That's what equilibrium means. But at this moment of time, the forward rate exceeds that of the reverse rate because we want to make more products, right? Make products in order to adjust that Q back to K. But let's think about it. We are adding what substance here? H2, which is a reactant. So let's go back to the rate laws for a second. So at equilibrium, these are equal, but we're not at equilibrium. Just know that this is the rate law for the forward reaction. That's the rate law for the reverse reaction. So based upon these equations that I have in front of you, does the forward rate change when H plus concentration increases? Yes, it does. We increased H plus, so shouldn't the forward rate increase? Yeah. What about the reverse rate? Does the reverse rate change when we add more H2? No, it doesn't. Why doesn't it change? Because H2 gas is not a part of the reverse reaction rate law. All right, so that's the big thing. Oftentimes students will say, oh, if you add H2 to get it to the product side, they'll say the forward rate increases and the reverse rate decreases. That's not true. It's only the forward rate increases. The reverse doesn't change. And the reasoning is because we're changing concentrations, all right, and it's only going to affect the forward rate, not the reverse rate. So yeah, okay, so here, why has N2 concentration decreased relative to its initial equilibrium concentration? A, B, or C? What do we think? only one of them should make sense. Only one of them should make sense. This is another misconception folks have. So the reason N2 gets consumed is because we added H2. That's the only reason. Because Kc is always a constant. We didn't change the conditions where K would change. K never changes at a certain temperature. The only way K actually changes is if we change the temperature, okay? But just changing concentrations of things doesn't actually change K. All right, a lot of concepts coming together, all right? And chapter 14 was tough. And now we're relating it to another type of K. All right, so let's do another one. Suppose more NH3 is added. All right, so that's what this line is right here. So we're at equilibrium, bam, we add some NH3. Which way does the reaction have to go? Has to go to the reactants. That's the part everyone can do. It's the everything else that's a little bit tougher. Okay, so if we go to reactants, does everyone see that we've moved to reactants? When we add a product, we have to shift to the reactants to make up for it. All right, so if we move to the products, let's predict how these graphs would look. What would NH3 do? It would have to go down. It'd have to be consumed, right? In order to make more product, or sorry, more reactants. It has to be consumed. So it has to go down. What about H2? It will do what? It goes up, yep. So I don't know how my lines are going to be like that. And then what about N2? It goes up. Does it go up less or more than H2? Why? Yeah, so it goes up less than H2 because we only get one, oh, that's a bad line. We only get 1 mole of N2 for every 3 moles. So essentially you make 3 times as much H2 as N2. So it goes up, but not as much. Right, we see that? All right, do I have a question here? No. So when this happens, when we reduce the amount of NH3, right, NH3 concentration just instantaneously is going down. Which rate, overall rate, is changing? The forward or the reverse rate? Which one? The reverse rate. Why only does the reverse rate change? Yes, NH3 is the only one that's involved in the reverse rate. There's no NH3 component in the forward rate. That's why it doesn't change. So does the reverse rate decrease or increase when we remove NH3? Does it go down, up? Remember, K staying constant. This number we're saying goes down. So if this number is a smaller number, the overall rate should go down. Okay, now let's think if that makes sense. If at this moment of time the reverse rate decreases, but your forward rate stays the same, does that end up in an overall production of more reactants? If we are saying that the rate of our reverse is actually now less than our rate forward, does that have us end up making more reactants, which is what Le Chatelier predicts? Yes, it does. Because the reverse rate, it's like saying I'm going up an escalator, okay? We're going at the same speed. So at that point in time, we're at equilibrium, right? But I'm saying at this point in time, my reverse rate is slightly slower. So that means the escalator slows down a little bit. Which way do I start moving? I start moving in one direction until I establish equilibrium again. That's kind of the idea here, that now the rates are unequal, so I can shift the reaction to the reactants, and that's where I want to go. The reverse reaction, oh wait, is this right? Did I do it right? Wait, no, that doesn't make sense. Wait, give me a second. Oh, that's why you're all confused. We added NH3. I thought we removed NH3. Why didn't anyone say anything? Wow, I just wasted like 5 minutes. I'm sorry. We are increasing product concentration. Okay, yes, so I started messing up right here. Yes, right here. This arrow is wrong. Y'all gotta yell at me. I heard whispering, but I thought you were all just confused, which you were. So this is wrong. Based upon this slide, NH3 concentration is going up. Yes, I'm very, very sorry. So just forget everything I said in the last 5 minutes, and we'll go through this again. If NH3 concentration is increasing, which overall rate is changing? The forward or the reverse? The forward? Is NH3 in the forward rate law? It is only in the reverse rate law. So if this number changes, this number, rate, goes up. If NH3 goes up, this goes up. So now I'm saying we're not at equilibrium anymore. I'm saying the reverse rate is larger because this is larger now. Okay, now it should make sense? Yes. Okay, so now we're saying, hey, the reverse rate, this process going from here to here is faster than going from this direction to this direction. So what we will see overall instantaneously is we make a little bit more reactants until we establish equilibrium again. Now do you see it? Yes. And the question is, when your reverse rate is larger, faster than your forward rate, is that consistent with what Le Chatelier's principle predicts? We add more product, we get shifted to the reactant side. That is consistent with the forward rate being larger than the reverse rate. All right, let's do another one. It's this one. Let's suppose we remove NH3. This is what is the same thing, all right? But regardless, we remove NH3, which way will the reaction shift based upon Le Chatelier? Towards the products, yeah. We removed NH3, okay? We have this void. The reaction wants to make up for it, so it's gonna push it to the product side. So we're gonna make more NH3, so my graph's gonna look like that. And N2 and H2, are those gonna be consumed or produced? They have to be consumed, right? Because they're reactants. In order to push to the product side, they have to be consumed. So it's gonna look something like that, and H2 will look like that, something like that, okay? In order to push to the reactant side. But again, let's base this on rates. If NH3 concentration goes down, which rate is affected? The reverse. Why? It's the only one with NH3 concentration in it. That's why. So if this value goes down, NH3 concentration goes down, rate reverse goes down. But does forward rate change? No. No, it doesn't. So now it's this way. So is this relationship consistent with what Le Chatelier's principle predicts? The forward rate is faster than the reverse rate. Overall, we see production of more products, and that is consistent with it because the forward rate is faster. Just instantaneously until we reach equilibrium again. All right. So that's relating it again to rates. Okay. Oh yeah. Okay. So this is the same question. All right. Okay. Basically. Okay. What happens when N2 is removed? Which one is it? It's only one of them. What do we think it is? B, the second one? Do we agree? It's the second one? Okay, let's walk through it. N2, we're removing N2, so N2 concentration is going down. So of these two reactions, or sorry, these two rate laws, the forward rate law and the reverse rate law, which one's going to change? The forward one, is it going to go up or down? Down, because this value is going down. So does the reverse rate change at all? No, because N2 is not in the reverse reactions rate law. So in this case, because N2 is going down, it would look something like that, okay? And so we would see, I guess, what does Le Chatelier predict will happen? It will, the reaction shifts what direction? To reactants. Is that consistent with what we just said right here? That because we're reducing N2, rate forward's gonna initially go down, so then rate reverse is kind of gonna overpower it. That is consistent with making more reactants. See how it all comes together? And it's really based upon the idea of what Kc is. Equilibrium constant is just the rearrangement of two rate laws for the forward and the reverse, where we have the ratio of the rate constants equal to that of products over reactants. Basically, these are basically all the same equation, just over and over. All right, so those are concentrations. Oh, I guess we can use Q also to help us here. So here's the same equation, okay? What if we remove NH3 from this reaction? Which way will the equilibrium shift if we remove NH3? To the products to fill it up, okay? So let's just pretend like we calculated Q. All right, yes, it shifts to the right to more products. So remember, K is equal to products over reactants. So if we instantaneously remove NH3, does K, when we calculate K to calculate Q, does it go up or down? If we remove NH3, which is a product, does that number get smaller or bigger? Smaller. We're removing a product, so we're making the numerator smaller. So that means Q is actually smaller than K at that moment. Does that make sense? Because we're removing NH3. And so in that case, since NH3 is going down, that's a product, we would say that the forward rate is faster than the reverse rate in that case. And so another way to think of it is if Q is smaller than K, right, products over reactants, we need to make more products to make up for it to get it back up to K. So Q works also to help us predict which way things go. So let's do one more. Let's see, is this at equilibrium? Using these numbers. So here's K expression. So how do we calculate Q? We plug in the numbers, but what's the significance of Q again? It's just not at equilibrium. So when we plug in these numbers, it may or may not be that 0.3 number. So this would be what? 2 squared over 6, so 4/6. Wait, is that right? No, it's not. No, it's super wrong. It's H2 cubed, so it's 6 cubed. All right, so it's a really tiny number. 4 over 216, or that's equal to 0.018. So that's Q. So is Q greater than or less than K? Less than K. So to me, that's saying I have too much what? Too much reactants. Yes. Too much reactants. Too much reactants. So based upon that, what happens? Which rate changes? Only one rate law contains reactants. Which one is it? The forward. So if we have too much reactants, rate forward is going to increase. So A is the correct answer, only A. Rate reverse is not affected. Okay, not affected because the reverse rate doesn't have reactants in it within there. All right, so there we go. All right, so that is concentration, all based upon basically rate laws, but Le Chatelier's principle still gets you in the right direction. The big jump here is, can you relate it to rate laws? That's kind of like the big jump. All right, so now we'll look into pressure. What happens when we change pressure of systems? Okay, so we can calculate Q for pressure systems as well. I will note here, when we are changing pressures, we're typically changing the volume of our container, right? Because pressure is proportional. Partial pressure of your reactant or product is proportional to N over V, which is basically concentration. So if we change the volume of your container, we're drastically changing the partial pressure of a gas. So we will stress equilibriums when we change volumes of our container, but not when we add an inert gas. Yes, we're increasing the total pressure of the system, but we're not changing the partial pressures of each of the components. All right, so here is just a generic gas phase equilibrium, the conversion from N2O4 to NO2. All right, it's the same idea. Forward rate equals reverse rate for this equilibrium process. We can relate it to the rate laws as well. This is forward, that's reverse. Questions regarding gas phase equilibrium, Kc to Kp conversions, I have to give you temperature in order to do that conversion. So just know that. So I have the answer here. We've already done examples like this, Kc to Kp. And the whole idea here, to do this equation, you have to get the change in moles of gas in your specific reaction. How do you get delta N for a gas phase reaction? What is this value? Well, I told you that it's 1, but how did I get 1 for this specific reaction? It's the number of moles of gas of products minus number of moles of gas of reactants, yes. Okay, so it's 2 minus 1. That's delta N in this example. All right, that delta N will help us in other ways too when predicting how gas equilibria shift. All right, so basically, and I kind of mentioned this before, qualitatively with Le Chatelier's principle, is if you reduce the volume of your container, you considerably increase the partial pressures of your substances, right? Right? Like decrease volume, increase pressure. That's Boyle, or I forget what law that is. I don't know. So pressure increases. So the idea is with an equilibrium, Le Chatelier's principle says the system wants to relieve that extra pressure. So you go to the side of the reaction with less moles of gas. That's what people see qualitatively. That helps you predict the direction qualitatively. But we'll actually look at the details and actually calculate Q. And we get the same idea. Versus if you increase the volume of your container, you reduce the reduce the pressure of all your gases involved in your equilibrium. So if you reduce the pressure, the reaction wants to adjust itself by pushing to the direction with more gas to kind of make up for that. So here, this is kind of like my way I remember how to do pressure changes, equilibrium. It's if you increase pressure, go to the side with less moles of gas. If you decrease pressure, go to the side with more moles of gas. That's basically it. And so it's very dependent on what the actual reaction is. Okay, but let's actually calculate it, okay? And I'll prove to you the same thing. Here I have this gas equilibrium with NO2 and N2O2. This middle piston, let's say that's at equilibrium, where we have these pressures. NO2 is 1 atm, N2O4 is 0.0826 atm. So if we calculate Q based upon the K expression, we would do the NO2 squared over N2O4. You see that? Okay, so this number squared over just this one. So when you calculate that with the numbers given, you get 12.1. So in this example, with these specific pressures, Q equals K, so we're at equilibrium. Do you agree? Okay, all right. So what if we doubled the volume of our container? So right now it's at 1 liter. If we double the volume, what will happen to the pressure? It'll halve. So what's the new pressure of NO2? 0.5. 0.5 atm? It halved. What about the pressure, partial pressure of N2O4? It also halves. So the pressure of N2O4 is 0.04 something, 413, right? And so those are my new pressures. Let's plug those into Q and see if it changed, all right? So we do 0.5 squared over 0.0413. And if you put that in your calculator, you get 6 something. 6. So how is Q different than K? It's smaller, right? K is 12, but now but when we increase the volume, right, double the volume, Q, when we recalculate pressures, actually went down. So based upon that, if Q is smaller than K, the reaction goes in what direction? To the products, because Q, you can think, oh, it's too small, you don't have enough products, which are the numerator. So the reaction has to go forward to make the number bigger, right? Is that consistent with Le Chatelier's principle? Let's think about it. Look at the reaction. We reduced the volume, increase the volume of our container, but reduce the pressure. The reaction shifts to the side with more or less moles of gas when we reduce pressure. If we reduce the overall pressure, the reaction wants to bring it back up, right? So we move to the side with more. We want to increase the pressure. So we move to the side with more moles of gas, which is what side? The products, isn't that what we just said about Q? Q is too small, we make more products. It's the same thing. Okay, let's do, you can imagine what happens when we reduce the volume and increase the pressure, right? If we reduce the volume in half from our equilibrium conditions, we do what to the pressures? If we reduce the volume, we increase the pressure by double. So now the NO2 concentration is what? 2, and then N2O4 is that number times 2, which is 0.16. This says 5, but I don't know. Is that right? I don't know. Okay, and then you just plug it into Q again, right? So we have 2 squared over 0.165. You put that in your calculator, you get 24. So in this case, oh, I guess I should say, how did we shift this when we went this way? So in this scenario, we reduce the volume, increase the pressure. So Le Chatelier's principle says if we increase the pressure of all the gases, the reaction shifts to the side with less moles of gas. We're squeezing all of the gas particles. The equilibrium will want to relieve itself of that extra pressure, so it'll move to the side with less particles of gas, which is the reactant side. So let's think about this in terms of Q. In this case, Q is greater than K. So we have too much what? Product. So the reaction needs to shift to the reactants. Is that the same thing Le Chatelier says? Heck yes, it is. That's it. Right? So everything, they're all related. They're just all different ways to think about it. All right. Sorry, this slide's a little bit wrong again. I messed up with the idea of inert gases. Inert gases do not change equilibrium. All right. So which of these equilibrium are unaffected by an increase in pressure or by decreasing volume of your container? Let me propose this question. What if I just had A goes to B all in the gas phase, and I say you increase the pressure of everything? Which way does the reaction shift? So in general, when we increase the pressure, I told you we go to the side with less moles of gas. Is there a side with less moles of gas? No. So this reaction is unaffected by pressure changes. It's unaffected by pressure changes because there's no side where it can relieve itself, so it's going to stay exactly the same. And kind of fun fact here, what is delta N in this? Delta N equals 0, 1 minus 1. So when delta N equals 0, Kp equals Kc. So in all of those ideas here, where delta N equals 0, Kp equals Kc, these are equilibria that are unaffected by pressure changes, like by changing the volume of your container. So in this case, we are looking for reactions that have a delta N of 0. That's kind of the trick here. So in A, what is our delta N? 2 minus 2, so it's 0. So this one's unaffected, right? That if I increase the pressure, there's really nowhere the reaction can relieve itself. It's going to have 2 on each side. What about B? What is delta N? 1 minus 0, so it's plus 1. All right. Okay. C is 4 minus 1, so it's plus 3. And then D, it's 1 minus 2, so it's negative 1. All right. So that's the strategy there. Do we see this? It's just products minus reactants, but it has to be the moles of gas. Those gases are really the only thing affected by pressure here. All right. So we did concentration, we did pressure. And again, with pressure, if you just recognize the reaction has to relieve itself somehow or like make up for what was lost, that will help you predict the direction. Now we're going to do temperature. Temperature. Remember how I said like an exothermic reaction, product, reactant, right? We treat heat as a product. I kind of lied. I lied. But let's just review that. It still helps us predict the direction, even though I lied to you. Okay, so here's my exothermic process. Is heat a reaction or a reactant or a product? For this first one, it's a product. So if we add heat, the reaction's going to go to the reactants. If we remove heat by cooling it, it's going to shift to the, which way? Products. Okay. How about an endothermic reaction? Where's heat? It's a reactant. Even though this is a lie, it still helps you predict the direction. Okay, all right. So if we heat the reaction, add heat, the reaction goes to the products. If we cool it, we go to the reactants. Very good. Do we see that? You see that? All right, so you just treat heat like a product or a reactant, but this is wrong. But we can still predict the direction. Okay, so with that in mind, let's see if we can't use our observations to determine whether a reaction is exothermic or endothermic, right? It's basically saying endo versus exo is just saying, is heat a reactant or product? So based upon these observations, we have a complex ion formation reaction where we can take iron 3, add thiocyanate, and we get iron thiocyanate, which is blood red, super red, right? So the reactants are yellow, the products are red. So based upon these observations, in a hot water bath, the solution turns yellow. In a cold water bath, it turns red. Is this reaction endo or exothermic? Think about it. Think about it. You're really quick about that. Exo. Does anyone not know where to start? Do we agree it's exo? Anyone think it's endo? Exo. Yeah, that was right. I think I asked this in 1110, and like, I think everyone said the opposite. Everyone said the opposite. And I was like, okay, let's break this down. So yes, I think it is exo. Yes, it is. So my idea is that the reactants are yellow, the products are red. So I ask myself, oh, when we heat it, we make the yellow thing. This is how I did it. When I add heat, we made the yellow thing. So I think, where does the triangle have to be on the reaction to have that happen? Right? That heat has to be a product. Do you see how it has to be a product? Right? If we add heat, we push it to the reactants. I don't know how you thought of it. Is that how you did it? Yeah, okay. Versus then if we cool it, is it consistent with that? When we cool it, it pushes it to the products, or the red side, the products. Is that consistent with what we're saying? Yes? Yes, it is consistent. So yeah, this would be an exothermic process. Do you see how we got that? Okay, let's do one more example. Oh, I shouldn't put this near the SO2. Let's do another example here. My demo, it's another one. It's actually the NO2 example. That I hear a lot of quiet. Like do we understand that it's on this side? So let's just pretend you don't know. Just try both of them. Put the heat on the other side and think about it. If I add heat and heat is a reactant, it should turn what color? Red. It should turn red. We should make product. But is that what we observe? No, it's not what we observe. So that means that, oh, I have to come up with a new solution that is consistent with my observation. Does that sound familiar? Sounds like chapter 14. Yeah. Okay, let's do one more, that demo. Where's that gas? N2O4. Okay, let's go back to this example. Let's see if we can't figure out if this reaction, that's what I have in these tubes, is endo or exothermic. So I'm going to tell you that N2O4 is white and NO2 is brown. All right, so I got my goggles. I have two containers here of NO2. So here's one. Here's the other. So I have my cold water bath here, so I'm just going to stick it in right there and then stick it in right there. So give it a minute. Okay. So I'm assuming the more brown one has more what in it? NO2. Okay, so based upon these observations, is this an exo or endothermic reaction? Maybe write it down, put the triangle on different sides, test it with Le Chatelier's principle, and see if it's consistent with what you see. So cold, this is cold. That one's hot. What do we think it is? Endo. So endothermic means heat is a reactant, or it's a positive number. Yes, it is a positive number, but again, think about like the significance of it. Endothermic reactions feel cold. Heat is a reactant. The reactant comes from us. Or sorry, the heat comes from us. We are the surroundings, so things feel cold. So yeah, is this heat being a reactant, is that consistent here with what we see? That when we add heat, we make more brown. We make more product versus the cold, we make more reactant, which is white or whatever. And the cool thing about this is totally reversible, all right? So I can take this one that has a lot of NO2 and then, whoops. Is it changing? Yeah? This one a little bit slower, but is it changing? Yeah, you can do this like forever, all right? All right, it's totally reversible, all right? So now we're making a ton more NO2 over here because we're adding heat, you know, we're making more of the brown stuff. This one's cooling down slowly, but you do see it getting lighter and making less NO2, all right? And then if I can switch them back, all right, and it'll do the same thing forever because we're either adding triangle or removing triangle from our reaction. Okay, so there's that. See, that's better. I like this demo better than the pictures I showed. Okay, that's what. There we go. All right, so let me explain to you why I lied to you. So I told you, like in these examples where when we change the temperature, right? I said treat heat like a reactant or product based if it's endothermic or exothermic. But remember what I said, big K changes with temperature. So although that explanation is consistent with our observations, it's actually a different reason why this reaction shifts to reactants. And it's because we're actually changing the value of K because we're changing the temperature. That's why the reaction shifts. It's because we're actually changing K. In all the other examples, we do not change K. Like, we're just changing concentrations of stuff. But in this example, when we change temperature, we change K. The reason is everyone's favorite, the Arrhenius equation. K, big K, is equal to products over reactants, but it's also equal to K, small k, F, rate constant forward, over rate constant reverse. All right? The Arrhenius equation tells us the sensitivity of rate constant. Reactions go faster when we heat them up, typically. K increases, didn't we say that before? But we also said in chapter 14, it's reactions with really large activation energies that are more sensitive to temperature changes. So I think the answer here is large. I think that's what it's supposed to be, okay? So in this endothermic reaction, which direction has the larger activation energy, forward or reverse? Forward has the larger activation energy versus this one is smaller. So if we raise the temperature, so K forward, right? K reverse. Based upon this idea, large activation energy is more sensitive to changes in temperature, meaning you'll see a more drastic change in rate constant. Which direction will increase more if we increase the temperature of our reaction? The forward reaction. Here's my analogy why large activation energies are more sensitive. Large activation energies, is that a fast or a slow reaction? Slow reaction. It's already slow. So if you increase at all a little bit, it's going to increase a lot. My analogy here is in high school, I took a weightlifting class. All right? And the majority of our grade came from our like 1 rep max, but it was like calculated. Like we repped like a bunch of times, like 10 times with the highest like, you know, bar we could. So when I started, we had to start somewhere, right? So I could barely lift up the bar. How heavy is the bar? 45 pounds? Okay, I could barely do it. So in the course of that semester, I got more confident like lifting, but I think I only put on like 5 pounds on each side. But because I started at such a low weight and made a little bit of improvement, I essentially guaranteed myself an A, all right? Because it was like a huge percentage increase in my 1 rep max versus someone who was already benching 200 pounds, okay? Like I went from 45 pounds to 60 pounds on the bar, and so that's like a nearly like 25, 30% gain. But for them, if they're already benching 200 pounds, in order to get a 30% gain, they have to put on a lot. So that's the whole idea. Like we're already starting with small numbers, small rates. That's with reaction rates that have really high activation energies as already. So putting it all together, we said that your forward reaction should be more sensitive to temperature changes. As temperature increases, what happens to K forward? It increases, right? But does K reverse increase? It also increases. They both increase, but which one increases more? Forward. It increases more because your activation energy is larger. Okay? All right. So both increase, but the forward increases more because the activation energy is larger. Temperature will always increase activation or rate constant, always. It's the Arrhenius equation. Okay. All right. Will the ratio Kf over Kr change, which is Kc? Does this change? Yes. Does it go up or down? Based upon what we just said, they both increase, but Kf increases more. Yeah. So So Kc should go up. Is this consistent with Le Chatelier's principle? So endothermic reaction, we have heat plus reactant, equilibrium, product. Is it consistent? When we add heat to an endothermic reaction, we make more product. When we add heat, K forward increases, Kc increases. Yeah, if Kc increases, the numerator is bigger, we make more products. All right? So we're making product a different way, and with temperature, it's because we are literally changing the value of K. See how they're all consistent? Beautiful. All right, let's do, oh yeah, consistent with Le Chatelier, yes. Okay, let's do this one. Okay, it's the same stuff, but here's a different type of reaction. Is this endothermic, exothermic? It's neither, because delta E or delta H here is actually 0. It's the same energy on both sides. Okay, so there's actually no change in energy for this whole process. So the activation energy barrier for both the forward and the reverse are the exact same. So let's think about that. When we increase the temperature, does the forward rate increase? Yes. Does the reverse rate? Do they increase different? No, the same. It's the same. All right? Because your activation energies are the same. All right? And so will your Kc change for this reaction? No, it shouldn't. Let's do one more. Okay, same questions, but we did endothermic. Let's do it for an exothermic reaction, just so we can just be really complete. And I want to show you that everything is consistent, right? Exothermic reaction. Okay. For this exothermic reaction, when temperature increases, we have K forward, and then we have K reverse. Does K forward increase? Yes. Does K reverse increase? But which one increases more? Reverse. Why? Larger activation energy. Yes, that the activation energy for the reverse is larger. Okay, so does Kf over Kr change? Yes. How? Kc will get smaller. Okay, so let's just write a generic exothermic reactant. Reactants, products. Exothermic is heat a product or a reactant? Product. Okay, great. So when we add heat, which way does the reactant shift? Left. That's what Le Chatelier says. If Kc gets smaller, what is more abundant then? If Kc gets smaller, the denominator gets bigger. Denominator is the reactants. See, it's the same thing. It's the same thing. It's just a different way of thinking about it. But again, I want to urge you, I feel like most people can get Le Chatelier. It's just like taking it to the next step and relating it to rates, the Arrhenius equation here. All right, so yeah, is that consistent with the our Le Chatelier principle? Yeah, it is. Okay. All right, have a good weekend, folks. Oh yeah, wait. I'm not an evil witch. And 14 and 15 are due this week, or this Sunday, right? So I'm gonna move it to Monday at midnight. I mean, you still have to do it, right, before the midterm. So I'm just gonna extend that pain and I'll move it to Monday for both of them.